So let's continue where we left off with graphing rational functions. So I will always ask these questions, not particularly in this order, but I definitely want to know what is the domain of the function. That'll tell us what we're allowed to plug into our t-table. To find domain, you set the denominator to either equal or not equal to 0. I like not equal to because that's what's really happening. X cannot be -2. You're supposed to write this in interval notation. So you're using parentheses around the infinities, because infinities always have parentheses, and parentheses around the -2, because the -2 is not included in the interval of your domain. So anything in this list you're allowed to plug into this function. So that means everything but -2. The second step was to calculate the x-intercepts. Okay, so to calculate an x-intercept, you always substitute y is 0. Well, in this case, y is your f of x. And we're solving this equation. To solve a rational equation that has a variable in the denominator, okay, you need to first multiply both sides by the denominator to get that x out of the denominator, and that cancels. Now, because there's a 0 over here, that's going to give us 0 equals 4 minus 2x. Okay, so we did multiply those together, but we just got 0. Now I'm going to solve for x by adding 2x to both sides of the equation, and then divide both sides by 2. That's going to give me x is equal to 2 in point form, which is what I want. That's the 0.20. Okay, so I'm going to go ahead and put that result right up here to remind me later when I erase this board that we found our x-intercept. It was 20. Number 3, they want us to find the y-intercept. To find the y-intercept, you always substitute x equal to 0 into your function. F of x is the y value, so I'm just going to call it y equals 4 minus 2 times 0 over 0 plus 2. So it gives us y is equal to 4 divided by 2, which of course is 2, and it gives me the 0.02. Again, I'm going to go ahead and include it over here in my list of information. Step 4 for this problem is to calculate the vertical asymptotes. Vertical asymptotes happen when the denominator is equal to 0, but this only happens after you simplify the function. So we can attempt to simplify this function by factoring a greatest common factor out of the numerator, which would be 2. That will leave us 2 minus x over x plus 2. Well, it turns out nothing cancels, so the factoring in the numerator was not required, but we needed to know. So I set now the denominator equal to 0 and solve, and I get x is equal to -2. Okay. Finally, we're supposed to find the horizontal asymptote. Horizontal asymptotes occur when you compare, well, the way to find them is you compare the degree of the numerator, which is 1 in this case, to the degree of the denominator, which is also 1. So the degrees match. Now, every problem we've done in this review, the degrees match. If they didn't match, then if the top is smaller, it'd be automatically y equals 0 is your horizontal. If the top is larger, it'd be automatically no horizontal. But they match like the other three, and so it would be y equals leading coefficient of the numerator, which is actually -2, divided by the leading coefficient of the denominator, which is actually 1. So I've got -2 over 1, which gives me y is equal to -2. Okay. All right, so I include this information. I've got x is equal to -2 for my vertical asymptote, and y is equal to -2 also for my horizontal asymptotes. Okay. Now, I'm going to erase all this information and replace it with an XY axis and a t-table and leave all of our details from solving right over here. So now I've replaced all the information with an XY axis and a t-table, and the first thing we want to do is include all of what we found on our XY axis. So I have an x-intercept of 2, 0. I have a y-intercept of 0, 2. I have a vertical asymptote, which I'm going to do is a purple dashed line at x equals -2. Remember, the graph is never allowed to intersect that line. And a horizontal asymptote of y equals -2. Now, the graph can possibly intersect that line. Okay, so let's plot some points. So the first thing I want to do is I want to make sure I include points between and beyond every vertical asymptote and x-intercept. So if I'm coming from the left side of the graph, the first thing I run into is a vertical asymptote at -2. So I need to plot a point or two to the left of -2. How about maybe -4 and -3? Okay. Then I need to plot something on the right. Now I've already got, I need something between my vertical asymptote and my next thing is my x-intercept right there. I've already got 0 plugged in, but it wouldn't hurt to have maybe -1 plugged in as well. Then I need something to the right of my x-intercept. Okay, so I need to know whether it goes down or goes up again. And maybe, how about 3? Maybe even 4. Nothing wrong with having an extra point or two. So 4 minus 2 times -4 divided by -4 plus 2 is going to give me 4 plus 8 is 12. Divided by -2 is -6. 4 minus 2 times -3 divided by -3 plus 2 gives me 4 plus 6, which is 10, divided by -1, that gives me -10. I don't have that on my scale, but we can approach that point. -1 plugged in is 4 minus 2 times -1 divided by -1 plus 2. That's going to give me 4 plus 2 in the numerator, which is 6, divided by -1 plus 2, which is 1. 6 divided by 1 is 6. 4 minus 2 times 3, divided by 3 plus 2. So that's going to give me 4 minus 6, which is -2 in the numerator, divided by 5, or -0.4, if you want to change that to a decimal. And the last one, 4 minus 2 times 4, divided by 4 plus 2. That's going to be 4 subtract 8, which is -4, divided by 6. So -2/3 are about -0.7. Okay, let's plot those points. -4, -6 would be here. -3, -10, much lower. But from there, I can tell that my graph is going down to approach the vertical asymptote, and then it's going to come up and flatten out here at the horizontal asymptote. Okay. It's not that weird bump that I have right there. Smooth that out. All right, other points. Something, we're plotting now because the vertical asymptote was right here in between. So this kind of divides that up into two separate pieces. Now -1, 6 up here. 3, -0.4. So 3, -0.4. And 4, -0.7 is just slightly lower. And I think that gives us a good feel for what's happening on that other side too. Again, we're approaching the horizontal asymptote at -2. We're approaching the vertical asymptote over here also at x equals -2, and it goes up forever. So this is our last problem where we have to graph a rational function in the review. By no means is this an exhaustive list. I noticed that none of these problems have a graph where you have to graph something with a hole in it, but there are some in the textbook, so I might be adjusting that soon. But anyway, so let's find the domain. The goal there is to set the denominator to not equal to 0, so I've got x squared minus x minus 6. That's not ever allowed to be 0. This will factor. I'm trying to find numbers that multiply to be -6 and add to be -1, and that's a -3 and a +2. So I'll set these separately to not equal to 0. So that means x cannot be 3, nor can it be -2. Okay? Now on a number line, if it helps you see that, x cannot be this value, nor can it be this value, but it can be everything else between and beyond. So my interval is -∞ to -2, union -2 to 3, union 3 to infinity. Okay, so there's my domain. Number 2, x-intercepts. Okay, so I set the entire function equal to 0 because I'm doing y equals 0. The goal is to solve for x. Well, I cannot do that while it's in a denominator, so that first step is always going to be to multiply both sides by the denominator, exactly the denominator, to get it to cancel. So this cancels with this. And on the left, 0 times anything is still 0 equals 6. Well, you can't solve for that. There's no solution for this equation. Either there's not equal 6, there's no variable left. So that means there's no x-intercept. So that's helpful information. We have no x-intercept. Number 3, let's calculate the y-intercept. To calculate a y-intercept, you let x equal 0. So y equals 6 divided by 0 squared minus 0 minus 6. So that's y equals 6 divided by negative 6, which is negative 1 in point form. That is the point 0, negative 1. Number 4, calculate the vertical asymptotes. Remember, that's when the denominator, after the function is simplified, is set equal to 0. Well, this function does not simplify. Don't cancel those 6's. You cannot do that. All of these are a sum or a difference, and you can't cancel part of a sum or a difference. So set this equal to 0. I factor it just as I did before. Set each factor separately equal to 0. It turns out I have 2 vertical asymptotes. I have one at negative 2 and one at positive 3. Finally, for the horizontal asymptote, you're comparing the degrees. Notice the the degree of the numerator is 0 because there's like an x to the 0 power sitting there. And the degree of the denominator is 2. The top is smaller. Anytime the degree of the numerator is smaller than the degree of the denominator, it's automatically y equals 0 is your horizontal asymptote. So what I want to do is include this information by where I requested it. Erase the board and get us an xy axis and a t-table going. So we do, to summarize, we have x-intercepts, none. Okay. Y-intercept, we had 1 at 0, negative 1. 0, negative 1. We had 2 vertical asymptotes, one at x is equal to 3 and another one at x is equal to negative 2. And we have 1 horizontal asymptote at y is equal to 0. Okay, give me a minute, erase this, and we'll plot some points. Okay, so I've replaced all of our work with an XY axis and a list of our information right here. And also, let's put a t-table over here. And now we're going to plot all of our information that we have. So we don't have any x-intercept, so I'm never going to cross this line. Okay, we do have a y-intercept at 0, negative 1, and we have 2 vertical asymptotes, one at positive 3. So I do a dashed line at x equals 3, and one at negative 2. So I do another dashed line at x equals negative 2. Now, my graph can never intersect these lines. It is possible that it can intersect the horizontal asymptote, which is y equals 0, but it won't in this case because we know we don't have an x-intercept. All right, now let's plot some points. This graph is going to split up into 3 different pieces. The piece on the left of the vertical asymptote, there's a piece in between the 2 vertical asymptotes right around here, and then there's a piece to the right of our x equals 3 vertical asymptote. So we've got some points to plot. I suggest at least 1 to the left of negative 2, but I think 2 is a good idea. So how about negative 4 and negative 3? And then notice we have a vertical asymptote, so we have a break right here. Okay, now something between our 2 verticals. So we've already got 0 plugged in, but how about maybe negative 1 and 1? And then we have another break in our graph, and then something to the right of x equals 3, like 4 and possibly even 5. Again, 1 point required. 2 points is a good idea. So I'm going to plug in. It's going to be 6 divided by negative 4 squared minus negative 4 minus 6. So it's going to be 6 divided by negative 4 squared is 16. That's going to be plus 4 is 20. 20 minus 6 is 14. In your calculator, you could calculate 6 divided by 14. And I get a decimal of 0.428. So I'm just going to put 0.4 because I can't graph any more accurately than that. So let's plug in 3. 6 divided by negative 3 squared minus a negative 3 minus 6. And that's going to give us 6 divided by negative 3 squared is 9. 9 plus 3 is 12. 12 minus 6 is 6. 6 divided by 6 is 1. So we've got a nice whole number there. I plug in negative 1. That's 6 divided by negative 1 squared minus a negative 1 minus 6, which is 6 divided by, that's going to be 1 plus 1 is 2 minus 6 is negative 4, which is going to be negative 3 over 2, or negative 1.5. Okay, then 6 divided by positive 1 squared minus 1 minus 6, 6 in the numerator. 1 squared is 1 minus 1 is 0 divided by negative 6, so 6 divided by negative 6 is negative 1. And then for our final piece over to the right, let's substitute in 4. So I have 6 divided by 4 squared minus 4 minus 6, which will give me 6 in the numerator. 4 squared is 16. 16 minus 4 is 12. 12 minus 6 is 6. 6 divided by 6 is 1. And then I plug in 5. That would be 6 over 5 squared minus 4 minus 6. I'm sorry, minus 5 minus 6. So that would be 6 divided by 25. Minus 5 is 20. Minus 6 more is 14. And then 6 divided by 14 is the same thing as it was earlier, 0.4. Okay, now let's plot those points and see what we've got. Negative 4 and a positive 0.4. It's going to take me right here. Negative 3, positive 1 is right here. Remember, that's all that I have to the left of that vertical asymptote. To me, that's enough to see that the graph will look like this. Again, approach the vertical asymptote going upward. We know it can't flip around and go back downward because that would be creating an x-intercept we don't have. So it has to go up, and then it's going to approach our horizontal asymptote. Okay, in the middle, we've got negative 1, negative 1.5, which would be here. And then positive 1, negative 1 would be here. Okay, and that makes that look like it's a horizontal line. It's not. It probably goes up and then comes back down. What I absolutely do know is that this doesn't flip back up, because again, it would be creating a vertical asymptote that's not there. And this also does not flip back up because we don't have any x-intercepts. I'm sorry, I said vertical asymptote, but I meant x-intercept. We do not have any x-intercepts, so I can't flip back up and make one that doesn't exist. And finally, on the other side of x is equal to 3, we've plotted the point 4, 1. And we need to plot the point 5, 0.4. And I think that's enough for us to see that our graph looks like that. So we've got several problems here where we're simply trying to calculate the vertical and horizontal asymptotes, and that's it. Okay, expect test questions like this on your in-class test. Now, vertical asymptotes, remember the rule is to simplify first. Okay, after you simplify, you set the denominator equal to 0. And those will be your vertical asymptotes. Verticals are always x equals a number. That's the form they should be in. Now, this does not simplify. Now, you may be tempted to cancel this x in the numerator and then the x in the denominator, but you would be canceling part of a sum. You can't do that. The x plus 5, that goes together and will only cancel together. So I'm just setting the denominator now, x plus 5. Equal to 0. I subtract the 5, and the answer is x equals negative 5. It's not just negative 5. It is required the x equals, because that's the equation of a vertical line. Okay? Horizontal asymptote, you're doing the 3 cases. You're comparing the degree of the numerator to the degree of the denominator. Okay, so the degree of the numerator versus the degree of the denominator. If the top is smaller, it's y equals 0. If the degrees match, then you do leading coefficient over leading coefficient. And if the degree of the denominator is smaller, then there is no horizontal asymptote. Well, in this case, these degrees match. I have a degree 1 in the numerator. I have a degree 1 in the denominator. So automatically I say y equals the leading coefficient of the numerator, which is 3, divided by the leading coefficient of the denominator, which is 1, so 3 over 1, or y equals 3. And we'll have a bunch of problems to continue this process with. Alright, so find vertical asymptotes. We simplify first and set the denominator equal to 0. So I'm noticing when I look at this numerator, There is an x in common to both of those terms, so we should probably factor it to see if we might possibly be able to simplify. And then in the denominator, I see that there is a 2 in common to both of those terms. Leaves x squared minus 25. Now, still nothing cancels, and that's okay, but we needed to do that just to be sure. So what I'm going to do is I'm going to set this denominator to equal to 0 and solve. Now, if you'll notice, this will factor more. That'll factor into x plus 5 times x minus 5. But still nothing cancels with what we had in the numerator. Now, to solve this equation, I can just simply divide both sides by 2 right now, and that 2 simply disappears. So x plus 5 equals 0, and x minus 5 equals 0. It gives me 2 vertical asymptotes. One is at negative 5, and the other is at positive 5. On the other hand, to find the horizontal asymptote, I'm comparing the degree of the numerator, which is 2, to the degree of the denominator, which is also 2. So if the degrees match, now you only do this when the degrees match. But if they match, then your answer is y is equal to leading coefficient of the numerator, which is 5. Ooh, didn't mean to do that. Hold on just a second. So the leading coefficient of the numerator is 5 divided by the leading coefficient of the denominator, which is 2. So I have 5 over 2, which is just that, y equals 5/2. You could write it as a decimal. I really prefer that as a fraction because we don't want to ever round that. Now where you put it, you might have to round it, but if you were to graph it, that's fine, just like that. And this problem looks almost identical to the last problem we did. I had to look at it twice just to be sure that it wasn't the same. It's not. There's a subtle difference, which makes a big difference in the answer. So to calculate vertical asymptotes, you again simplify first. This, just like the last problem we did, does not simplify, but we're going to treat it like a brand new problem. And the idea is you factor just to be sure. And this denominator factors into x squared plus 25 when you pull the greatest common factor of 2 out. Now, you can attempt to factor this again, but folks, x squared plus 25 does not factor. Why not? Because it's a sum of squares. A sum of squares doesn't factor. A difference, if that was subtraction, it would factor. So I set 2 times x squared plus 25 equal to 0 to find the vertical asymptote. So I divide both sides by 2, and the 2 simply disappears. Now I subtract the 25 over because it doesn't factor, so I'm going to have to do something different than I did on the last problem. I take the square root of both sides, don't forget the plus or minus, and I get plus or minus 5i. Well, that's not real, which means we have no vertical asymptotes. We can't have imaginary numbers for vertical asymptotes, therefore we don't have any. Horizontal asymptote, remember, is you compare the degree of the numerator to the degree of the denominator. They match again. Whenever they match, it's y equals leading coefficient of the numerator, which is 5, divided by leading coefficient of the denominator, which is 2, and we have y equals 5/2, just like we did in the last problem, so 5 over 2. Okay, our next problem. Vertical asymptote, we simplify first. Well, there's nothing that's going to cancel here at all, and so we just jump right in and set this denominator 2x squared plus 3x minus 2 equal to 0. That's going to give us our vertical asymptotes. We need to factor this if at all possible. You could play around with it, or you could use a technique like you're trying to find numbers that multiply to equal -4. How did I get that? By multiplying those together and add to be the middle number, which is 3. Numbers that would do that would be a +4 and a -1. Then you could rewrite the middle term, the 3x, with plus 4x minus 1x. And then the -2 just carries on over. See that trick? Then you do factor by grouping. Okay, so you pull the first two together and factor out the biggest thing that goes into both of those, which is 2x. That's going to leave x plus 2. And then we need to factor out the largest thing we can out of these two, which is just a minus 1, which also leaves x plus 2. And the one that matches, you can write in front. The one that's left, 2x minus 1, out here, is the second factor. Now you set each of those factors equal to 0, and you get negative 2. And when I set 2x minus 1 equals 0, I get 1/2. Okay, so I have two vertical asymptotes in this case. Now, horizontal asymptote, you compare the degree of the numerator, which is 4, to the degree of the denominator, which is 2. If the top is larger, there is no horizontal asymptote. Okay, so I'm not doing 5 over 2 in this case. Notice it's only when the degrees match do you do leading coefficient over leading coefficient. If the top is larger, and 4 is larger than 2, okay, then there is no horizontal asymptote. Okay, so our last problem of calculating vertical and horizontal asymptotes. So the vertical asymptote here, simplify first. We cannot cancel a 3 or an x with anything in the denominator, because there's not, just simply a factor of 3x in the denominator. So I set the denominator x to the 4th plus 2x squared plus 1 equal to 0. Okay, and then I factor this thing. Now, notice it's what we call a quadratic type. It's not quadratic because it's a degree 4. Quadratics are degree 2. But it is a quadratic type because that is like a square. That is like to the first power. And there's my constant. So when I factor, what gives me x to the 4th would go in the first spot. Well, that's x squared times x squared. Okay, what gives me 1 would go in the second spot. Well, that's plus 1 plus 1. If you check it by multiplying back out, you do get that. Now we would factor again if possible, because that is a degree 2, but that's a sum of squares, so it doesn't factor again. So I set the denominator equal to 0. I don't have to do it twice, because it is the same thing, but I want you to see them, and you know, you do look at those separately. But since it's the same thing, I don't have to do it twice. Now I subtract the 1. To get negative 1, I take the square root of both sides. So get plus or minus the square root of negative 1, which is plus or minus I, which is not real. So we have no vertical asymptotes. None. Okay. Now on the other hand, horizontal asymptote, I compare the degree of the numerator, which is 1, to the degree of the denominator, which is 4. Notice the top is smaller this time. Anytime the degree of the numerator or the top is smaller than the bottom, then it's automatically y equals 0. No calculation to do. You're not doing leading coefficient or leading coefficient because you only do that when the degrees match.